Good morning, everyone. So we're going to continue here in Chapter 6, talking about the hydrogen emission spectrum, what we can learn from it, and then how we can move away from it to talk about larger atoms. But one thing I wanted to point out, and to some extent I really don't find these problems all that fun to solve, but if you notice this peak here, this occurs at 656 nanometers, and the way this equation works is, Rydberg just tried to find an equation that he could somehow calculate that number 656 out of, from some sort of an equation. And the Rydberg constant for hydrogen, this is like a given value. So you would have this on a test if you need this. It's 1.097 times 10 to the 7 inverse meters. And so even the equation's given. Chapter 6 is kind of the first chapter where we're going to have a lot of equations given. So we'll have like the speed of light, lambda times nu is a given equation. If you need to use this equation, it's given. Or I think it's just on the packet regardless if you need it on the test or not. And this conversion factor here, or the constant for the Rydberg constant for hydrogen, is also a given value. And then I was mentioning that these transitions are all kind of arising due to some higher energy state transitioning down to the n=2 state. And we were seeing from what we had saw last time that the energy is a function of n, that as the n goes up for hydrogen, the energy of the atom is just increasing. So we have increasing energy as you go from N1 to N2, but then the energy it takes to go to N3 is a little bit smaller. It's actually a fair bit smaller than it was for N1 to 2. So N1 to 2, big difference of energy, 2 to 3 smaller. The n=4 state, even less energy to go up, the 5 state. And then eventually we're getting to, if you go to n=infinity, if you remember this equation, this is also a given value, but the energy as a function of n was equal to minus 2.18 times 10 to the minus 18 joules times that n value, 1 over that n value squared. So if you're going from n1, you can imagine going all the way up to n=infinity. As n's approaching infinity, what's going on is the energy of that electron, the energy of the atom, is approaching 0. And so that's telling you, or allowing you to understand, the ionization energy of hydrogen is about 2.18 times 10 to the minus 18 joules. So that this is approximately the energy it just takes to remove that electron. Now, I don't want to get too sidetracked by this because this isn't a big detail. This is maybe something we'll talk a little bit more about in Chapter 7, the next chapter. But if you multiply that energy by Avogadro's number to say, well, what's the ionization energy in kJs per mole? Convert it to kJs. This ends up being 1,312 kJs per mole, which is, very precisely the ionization energy of hydrogen. So from a really simple equation, we can calculate like a really important and observable property for hydrogen. And so we're going to see that this equation, we can think of an equation like this for hydrogen. We're not going to be able to come up with a nice equation for the other atoms, though. So this works well when we have one electron in an atom. And so this is just taking our electron, being close to the nucleus, and then making it so far away that it's removed from the nucleus altogether. And so if we want to calculate then, because one of the things I was talking about is how the transitions that we're seeing in the H atom emission correspond to the 6 to 2, the 5 to 2, the 4 to 2, and the 3 to 2 emission, that you can imagine the 6 to 2 difference of energy is a greater difference of energy than, say, the 3 to 2. And so the 3 to 2 has a relatively small difference of energy compared to the 6 to 2. And so you might be able to picture here that this should be the 3 to 2 transition of hydrogen, and then this should be the 4 to 2, this should be the 5 to 2, and then this should be the 6 to 2. Now, how can you support or show this? Well, again, just think about how the 6 to 2, the greatest difference of energy transition, leads to the greatest energy photon. This photon here, which we can see it on the screen, that photon there just has a greater energy. So remember how energy of a photon is hc over lambda. If we go to a smaller wavelength, we're going to a greater energy. So the H atom's losing a bigger difference of energy. That energy difference is what creates the photon. So it's one, and this comes back to the photoelectric effect. The idea of the photoelectric effect is you have one atom undergoing a change as you have one photon of light either being absorbed to ionize something like the photoelectric effect we're seeing with metals. Here we have H atom that's in a high energy state, one atom losing energy, creating or going into one photon. And so we can calculate the wavelength for one photon, take the wavelength, and let's try to calculate this for that 3 to 2. Let's try to calculate that 656 nanometer photon. So let's do this for the 3 to 2 peak. So the wavelength should be equal to 1 over the Rydberg constant. So I'm just dividing both sides by this, multiplying by the lambda to solve for lambda. So I'm going to divide by the Rydberg constant for hydrogen, and then times 1 over the n value squared. The n1 here is just a larger value, so I'm going to divide by 1 over the 2 value. So I'm going to put the 2 in over here, and then minus the 1 over 3 squared. And then I just need to plug in the RH. Again, this is 1.097 times 10 to the plus 7 inverse meters. So let's do that math real quick. So I take 1 divided by, and then like the parentheses of 1.097 E7, and then another parentheses, 1 divided by 2 squared, minus 1 divided by 3 squared. And so I do this arithmetic, and I get 6.56 times 10 to the minus 7 meters. 1 meter is a 10 to the 9 nanometers, so multiply that by 10 to the 9 nanometers to convert over into units, and that's 656 nanometers. So that's how we can calculate that wavelength that's associated with that particular line in the H atom emission spectrum, coming from the H atom going from a high energy state, the n equals 6 state, transitioning down to the n equals 2 state. Now, of course, you're probably sitting there thinking, well, why doesn't it just go to the n equals 1 state? It does. Some of the atoms do. Imagine you have 1 million atoms in the n equals 6 state. What ends up happening is some portion of them go to 5, and some of them go to 4, some of them go to 3, some of them go to 2, some of them go all the way down to 1. And once the molecules do get to the n equals 2 state, eventually they're going to go to the n equals 1 state. So these transitions down to the n equals 1 state do occur, but the issue is that this just happens to fall in the UV region. Like if we want to go back and resolve this, I don't want to because it just becomes, like we can go through the math problem as many times as we want, but this is going to correspond, if we do this, to 121.6 nanometer photon. So if we look at that n equals 2 to 1 transition, it's definitely in the UV region, not something you're going to see in the visible region. So we have 4 visible peaks that we can see in the visible region. Then we have a lot of transitions we could see in the UV region. And then if we go 3 to 1, 4 to 1, 5 to 1, those transitions just keep going to a greater and greater energy to a lower and lower wavelength, harder and harder to see. We're not going to see those in the visible region. And then you can even think, well, what about the 4 to 3s, the 5 to 3s, the 6 to 3s? What about the 5 to 4s? Those transitions, these are all in the infrared region. Those are all in the region that's too low of energy to see in the visible region. So again, those transitions take place. It's just if we say you're looking in the visible region, you see the 4 transitions. And then seeing those transitions led to the question of what leads to them, and it led to the development of models like the Rydberg model, led to the development of models like the Bohr model to try to understand the relative energies of hydrogen. So we looked at this slide yesterday. This is just showing that you could calculate the energy as a function of the n value of the electron is minus hc times the Rydberg constant. And then z is just the nuclear charge of hydrogen, so that's just 1 for hydrogen. So this equation here, this is also a given equation on tests that you can use if you need to use it. And so you can calculate a change of energy for the H atom. You can see how the H atom, if we go from, say, H atom n equals 6 to n equals 2, that's a loss of energy by the atom. So the atom's losing energy. Losing energy is emission. Where does that energy go? It goes into creating the photon that we can see evolving from that transition taking place. And then if you have the opposite, if you're imagining, well, what about a molecule in n equals 2? So imagine you have hydrogen n equals 2 and you want it to transition to n equals 6. Then the atom would have to absorb energy. We would have the absorption of energy. So we have to have energy absorbed to go upward. I think we're going to highlight this on the next slide too. So we have energy that has to be absorbed. Maybe we can have a photon absorbed. We could have energy absorbed in the case of high voltage energy. That's what's going on in the real light sources. You have a high voltage source supplying the energy, creating our hot atoms, and then light's emitted off as they're cooling back and coalescing back towards their ground state. Okay, so the values in the Bohr model here are n equals 1 or n equals 2, 3, etc. on upward. These are just showing us the relative energy as a function of n is increasing as we go up in n value. You can imagine going all the way up towards n equals infinity. This is just going to H plus the electron being fully removed. The n1 closest to the nucleus, n2 further away, n3 further away. So as n increases, the electron's just moving further away from the nucleus. And then a positive delta E for the atom means energy is being absorbed. So to go from n1 upward, that's absorption of energy. And then if you have a molecule, say an N2, coming downward in energy, that corresponds to a loss of energy. That's energy released by the H atom given to the photon. So here you'd have emission of photons going downward, and going upward you'd have the absorption of photons, or sometimes just the absorption of energy like high voltage energy to create those high energy states. Now, it turns out that if you use high voltage energy to create atoms in these high energy states, that they're almost always going to emit photons on the way down. It's really hard for them to emit energy in any other way other than the emission of photons. So you'll see light sources created by all kinds of different substances as they absorb energy, go to some high state, and then as they coalesce back to their low energy states, light's given off in those processes. So if you have other light sources, if you use helium, and I think you guys will do this in lab, you might look at like a helium lamp has a different color because it just has different wavelengths of light that it's undergoing transitions of. If you have a light source like the light bulbs in the room, they have the emission of basically every wavelength in the visible region, so they appear to be a white colored light, as opposed to a hydrogen lamp, which I don't want to flip back, it screws up the video, but if I go back, if you look at the H atom emission, most of the transitions are close to the 400 nanometer side, and so light's going to appear to be more on that violet color light side than it is on the red light. So if you have a light source that has more red photons, it's going to appear reddish. If you have a light with more photons on the blue side of the spectrum, more blue-violetish. Okay, and so we can have a question like this, like just a conceptual question of which transition below for an electron in the H atom causes the greatest wavelength of light to be emitted. So think about this one for a minute. So if you're thinking about transitions, think about if you want a high energy state transitioning to a low energy state to cause emission, or the opposite, and then think about how the wavelength of light is associated with these transitions. Do you want the transition to be far away or close together to give a greater wavelength? So I'll give this question a moment or two, and then we'll go over it. All right, so let's think about this one. So if we go from 2 to 3, so if the H atom transition from a low energy to a high energy state, energy has to be absorbed, not emitted. So it can't be the 2 to 3 transition, can't be the 3 to 4 transition, because those transitions would require the H atom to absorb some wavelength of light or absorb some form of energy, not emit energy. So these transitions here, the 2 to 3, the 3 to 4, these can't be the answer because these require the absorption of energy, not the emission of energy. And so then if we think about the 3 to 2, the 4 to 3, these transitions here do occur with the emission of energy. So the 4 to 3 versus the 3 to 2, the 3 to 2 you can see has a greater difference on our scale, has a greater amount of energy difference that's going to be lost by hydrogen. So this transition here is going to lead to a lower wavelength than the transition from the 4 to 3, which has a smaller energy difference. So a smaller energy difference is going towards the infrared, going towards a lower energy. So lower energy transition means a higher wavelength. So the energy of our photon is equal to hc divided by the energy, hc divided by the wavelength of the photon. And so if the energy of the 4 to 3 is going to be smaller, because it has a smaller difference of energy than the 3 to 2, then that's going to correspond to having a greater wavelength. So as wavelength increases, the energy of our photon's dropping. This is why as you go from low wavelength to high wavelength, we're going towards the lower energy of the electromagnetic spectrum. Go to longer wavelengths past the visible, so wavelength goes up, you get to the infrared. Keep going up, you get to the microwave. Keep going up, you get to the radio frequency. That's good. We have a bunch of radio frequencies bouncing around the room, really low energy forms of electromagnetic energy. We don't want gamma rays bouncing around the room because that's the high energy side of the spectrum. So if you go past the visible into the ultraviolet, we're just moving towards the high energy side of the electromagnetic spectrum. So the lower energy transition, the greater wavelength transition, is the 4 to 3. So that's the emission, and that's the lower energy emission for these given transitions. So as you notice, as you go from n equals 1 to 2, big energy difference, to 3, not as much, to 4, not as much, to 5, not as much. So the energy difference of each successive n value is becoming smaller and smaller. So like the 4 to 5 difference even smaller, 5 to 6 even smaller, and eventually that's what allows us to get up to ionize. It's what allows us to get up to the electron finally removing itself from the atom. So infinity is just the idea where we fully ionized that electron and removed it from the atom altogether. Okay, so a little summary here, or a few final notes would be that our Lyman transitions, that's what we call the transitions that end in the 1 state. So the Lyman transitions are the one that end in 1 but start in 2 or greater, and these are in the UV region. So those are in the high energy portion of the electromagnetic spectrum. The Balmer series are what we call the visible photons that are occurring from transitions ending in 2. So the Balmer transition, I don't know if you ever need to know that word, but we call the Balmer transition the ones that end in 2. The transitions that end in 3, these are in the infrared region. And what I think is more important is just kind of seeing the transitions that end in 1. Big difference of energy, high energy, that's ultraviolet. The visible in between, the 6 to 2 all the way to the 3 to 2s. And then the transitions ending in 3 or greater, those are going to be in the infrared region. So IR, visible, and then UV. And then a few limitations to talk about here, the Bohr model. That one, this equation's nice, this approach is nice for one atom. So this whole approach of calculating specific changes of energy as a function of the n value, thinking of the electron residing in some type of, maybe you start to think of like an orbital nature here, maybe you're getting that from the Bohr model, but we're really limited to hydrogen mathematically. And so this also doesn't describe why we can't have values in between n equals 1 and 2. It doesn't really tell us at all why the n has to be a whole number. We also can't describe multi-electron atoms with this approach, and it also doesn't describe what we will see better described by other approaches, the wave-like nature of matter. So there's really no description here of the electron behaving like a wave. It's treating the electron almost too discretely, as if we know precisely it's here, or it's here, or it's here. What we're going to see on the next couple slides is that we have some important principles, like we have an uncertainty principle where we don't really know where the electron is. So we don't really know it's here versus here versus here, and n1 versus 2 versus 3. We're going to start talking about probabilities, that the probability as n increases just means the probability of where you find the electrons becoming further away from the nucleus. So we're never really going to know exactly where the electron is around an atom. With the Bohr model, you may think that you do. So there's a few limitations with this model, but it does describe these transitions through the H atom perfectly. If you ever get to work with a lab that ever deals with H atom emission, I mean, the transitions occur exactly where you calculate them to be. So that's exciting for the one atom of hydrogen, not so exciting for all the other atoms and molecules you might work with. And so let's get past hydrogen. So let's talk about the wave nature of matter. So de Broglie, or I suppose in French his name's actually pronounced de Broglie, which I find odd to pronounce that way. But in 1924, theorized that if light can behave like matter, so if light has this wave-particle duality, what if the electron has a wave-particle duality as well? I think we would classically think of the electron as a particle since it carries a mass, but what about the electron or small particles behaving as a wave? And so this wavelength here, I usually call this the wavelength, the de Broglie wavelength, because this is the wavelength associated with matter as a function of Planck's constant divided by the mass of the particle times the velocity of the particle. This equation here, you have to make sure that you treat this problem here for problems dealing with matter, not for light. So this wavelength here is not about light. So if you see this equation about a wavelength of light, it doesn't imply that light has some mass associated with it. It's implying that this would be the wavelength of a matter. So imagine an electron being fired across a potential where the potential is some distance away, and then this wavelength is the electron traveling like a wave on its trajectory from one point to another. And so this is just the wave nature of matter. And what we're going to see, and we'll see a quick example comparing a baseball to an electron, that if you have a really light particle with a really high velocity, then it starts to have a wave behavior that's important to understand the description of that particle. If you have a more massive particle, then this is completely irrelevant. And so we'll look at that comparison in a moment. Let's first introduce another idea, the uncertainty principle from Heisenberg, of course made popular by Breaking Bad, which we should almost just have a whole course in watching that in general chemistry instead of this stuff. But if you haven't seen the series, highly recommend it. But this is probably the most misused and miscited equation and idea in all of chemistry and all of science, I believe. But the uncertainty principle is talking about the uncertainty in the position of particles. So the uncertainty in the position of a particle is related to the uncertainty of the mass and the velocity of the particle. And there's a fundamental relationship that falls out of quantum mechanics that the uncertainty in the position multiplied by the uncertainty in the momentum must be greater than or equal to h divided by 4 pi. I recall sitting in an English class as a student, and I really, truly heard a student in the class I was in cite this equation for the inability to know anything. So I was like, that's fascinating. I said, what part of this equation tells you you can't know anything? And so I actually went up to the board and wrote the equation on the chalkboard, and I said, this is the uncertainty principle. What does this mean you can't know? So this equation is just relating to the precise knowledge of the position and the momentum of a particle. And so again, imagine you have, sometimes it's like worthwhile just to picture a baseball. You have a pitcher throwing a baseball, and so you can see the baseball where it is. You don't see it as a fuzzy kind of particle as it goes from one spot to the next. You can see it clearly as a particle, and so you can imagine that it has some position x. The uncertainty is delta x. It's how precisely do you know where that particle is. So the delta x is the uncertainty in the position. If you knew the position was, let's say, 15.5 meters down the place where the baseball was thrown from, the plus minus on that value is the uncertainty. So it's not the position itself, but it's the plus minus. So let's say you have a 0.2 meter uncertainty. So let me rewrite this. 15.5 plus or minus 0.2. I keep writing a different number than what I'm writing. So 15.5 plus or minus 0.2 meters. This is the uncertainty. It's how well do you know the position. So you can imagine the greater the better you know the position, then the smaller this value is. So the more precise we know that position to be, the smaller that value goes. And so for a baseball, we can see it with our eyes, know pretty much exactly where it is. You can see it as a discrete particle. And then you can also know the velocity. The velocity has an uncertainty associated with it. So this is going to be on the next slide where we can work through some math problems. But you might imagine you have a 95 mile an hour fastball. Maybe your uncertainty is 2 miles per hour. But it's this uncertainty that matters. And so we often will rewrite this as the mass of the particle times the uncertainty and the velocity. And so the mass of the particle is usually a constant and not changing, or not part of the uncertainty. So usually you're pretty certain in the mass of the particle. It's the velocity's measurement that is what you're actually measuring here. And so you can write m delta v as the uncertainty and the velocity as it relates to the uncertainty in position. And so you can kind of go through problems where you can have a big particle and you'll see you can know very precisely its velocity and very precisely where it's at with no issue. For objects that behave quantum mechanically that are so small and have such a high velocity, it's going to be the tandem of those particles, small, high velocity, and the uncertainties associated with them that give us an issue with the inability to precisely know where exactly that particle is and what its velocity is. And so that's going to lead to an orbital or a probability sort of description of where particles are, where electrons are. Okay, so these two problems here, if you ask me, these are meant to show the ideas here. So we rarely ask these math questions on a test. So let's just try to treat this as, can we compare what that de Broglie wavelength looks like for a baseball and compare it to an electron? And then let's try to think of an electron with an ordinary velocity, kind of like an average velocity for an electron. And so for the de Broglie wavelength part of the problem, what we need to know is the mass of the particle, and we need to know the velocity of the particle. And so I'm also trying to think of a baseball with the speed that we can maybe picture, so 95 miles an hour. I don't care about the conversion, that's 43 meters per second. If I had just said 43 meters per second, you would probably not know what that speed was. So that corresponds to a fastball. And so the de Broglie wavelength for the baseball, I need to take Planck's constant, joules times seconds, divide by the mass of my particle in kilograms, the velocity in meters per second. The reason why I want these specific units here is just so the units work out. So a joule is a kilogram meter squared per second squared. And so putting the units into joules times seconds, we want the mass of the particle into kilograms, we want our velocity into meters per second, so that we're canceling everything out here except for one of the units of length being the meter. And so then we plug in the math for the baseball, and the baseball has such a small wavelength. Like the wavelength is so small, that just means it's traveling in a straight line. This is just the definition of a particle traveling in a straight line path. So the baseball's thrown, it's not oscillating up and down like a wave, like you think of a photon. So it's not traveling with a real wavelength. So this is such a small wavelength that it's effectively no wavelength, that this is just the idea of a straight line trajectory. And so then you do this for an electron, and the only difference between the electron and the baseball is the mass of the electron is much more low. So we have 9.109 times 10 to the minus 31 kilograms. That's the mass of the electron. That's always a given if you need to do the math. But like I said, this isn't a common problem that we usually give you in math form. And then we want to plug the velocity in, because we're just plugging into h over mv. And then again, mass in kilograms, so the kilogram cancels, meters per second. So everything cancels except for one of the lengths of unit being the meter. And so now the electron's wavelength ends up being 2.4 times 10 to the minus 10 meters, which if we convert that to angstrom, if you remember, 1 angstrom is a 10 to the minus 10 meter. So that's 2.4 angstrom. So now you think of an electron spinning around an atom. This wavelength is on the order of the diameter of an atom. So this becomes an important wavelength for the motion of an electron. And so what this is telling us is electrons, they're going to have a wave-like behavior associated with them if we're going to want to understand them. So we're going to want to think of electrons behaving as particles, but also as waves. So this is telling us there's going to be a wave nature to the electron's trajectory. And then what about the position of the electron? So we're just trying to plug into this equation. Here we could rewrite it as delta x is m delta v greater than or equal to h over 4 pi. And so what we're going to try to compare is the uncertainty in the position. We're going to try to calculate what delta x must be equal to or greater than. So delta x has to be greater than or equal to h divided by m, uncertainty and velocity, and then times 4 pi. And then this just being a fundamental relationship for any particles, but just a relationship that's really important for the small ones that have a high velocity. And so then if we plug this in for a baseball, our uncertainty in position, so again, you're picturing a baseball on its way from the pitcher's hand to the catcher's glove. You can see it with your eyes. You can imagine measuring the velocity and having the uncertainty in the velocity. It's the plus minus that matters. It's this plus minus 1 here. This is our delta v. So when we plug in our h divide by 4 pi times m times delta v, it's the uncertainty in the velocity. For the baseball, it's just whatever comes after the plus minus, so it's 1 meter per second for the baseball. And so if we have an uncertainty in velocity that's ordinary, plus or minus 2 miles per hour is a very ordinary uncertainty in velocity, we can be very, 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 very precise of where the baseball is. You know, like we could be precise to the 34th decimal place on where the baseball is. So in other words, we have no problem with finding that baseball and then knowing its velocity. Okay, so for ordinary particles, this isn't a concern. This doesn't mean when the ball is thrown, it appears to be a ball of fuzz. If we could throw an electron, it would just look like a static, like it would just be a discrete particle. Then it would have this like almost like cloud that we would be able to see. We can see that when we plug in the electron part to our calculation. So h over 4 pi mass of the electron, a lot smaller. And then the uncertainty is this value here. So the average speed of an electron in an atom, I believe, is about 3 times 10 to the 6 meters per second. So if we take an uncertainty of about 0.1 meters per second, plug that in here, and then do the math, we end up getting 5.8 times 10 to the minus 10 meters. The uncertainty is 6 angstrom. So in other words, we have an ordinary electron with an ordinary velocity. We have an ordinary measurement of the approximation of the certainty in that velocity, and we have no idea where that electron is now. So like our uncertainty now becomes the thought of a cloud or a probability diagram or like a probability distribution. So we start to think, okay, we're gonna have to like picture this as orbitals. We're gonna have to go to more of an orbital nature of matter or more of a wave description as well on top of that orbital description. So the conclusions of these two equations or these two ideas are that electrons are gonna be better thought of as behaving like waves and then behaving as waves we don't precisely know where they are at any given moment. So we're gonna have to think of probability distributions. And so this is going to lead to orbitals. This is going to lead to the things like 1s2, 2s2, like the sort of electron configurations, so ground state electrons residing into different types of orbitals. Okay, so one little picture for quantum mechanics, and the book does mention this equation, h psi is equal to E psi, the Schrodinger equation, just to kind of get into this description of the wave function of a molecule or an atom. So if we can try to understand the wave function, we can operate on it with the Hamiltonian operator and return the energy of that wave function. But it also just tries to get into the description of waves. And one of the things I like to think, if you imagine an electron that's traveling in a circle, and then you have these like ideas of pinch harmonics, you can think of a pinch harmonic from physics of having, no nodes. That's our fundamental. You can have one node in the middle or two nodes. Imagine this bent around the radius of an atom. This starts to be why you have to go from N1 to N2 to N3. In order to maintain the number of nodes around the atom to be a whole number, if the number of nodes have to be a whole number to maintain a wave-like description and path around the atom, then we're going to have integral values for things like that n value. So the n value is just kind of describing or related to the idea of these nodes and maintaining nodes as we're sort of having electrons spinning around atoms. And so I think this helps us maybe understand why the n value goes from being 1 to 2 to 3, just to maintain a number of nodes that's a whole number to maintain an actual spinning around the atom and not have the electron fly off and get off course. And so, yeah, this is what we're describing here. So the Schrodinger equation then allows us to sort of say, well, what type of waves can we determine or get out to describe the wave nature of matter? And so we start to get things like 1s orbitals to describe things like H atoms in their ground state. So we can start to sort of get a picture of what type of orbitals or waves you would need to sort of describe matter through this equation. So we get sort of the wave nature of matter, an orbital picture falling out from this analysis. And so we get things like 4 quantum numbers that help us try to describe the sort of position, the shape, the orientation, and then the spinning of electrons in their different types of orbitals they can reside in. And so then we have things like the principal quantum number n. That's what we were seeing in the Bohr model. N's related to the size of the orbital. So as n goes up, the orbital is growing larger. So n takes on whole numbers from 1 to 2 to 3 on upward. So the smallest n can be is 1. And so then our angular momentum quantum number L is describing the shape of the orbital. And so L can take on values of 0 to 1 to 2 all the way up to n minus 1. And so as we get shape, starts to be things like S shape, P shape, D shape. If L is 3, we get F shape. What does that mean? Well, this starts to look like the S shape of our orbital is like a spherical shape. So our greatest probability is just like in all sort of 3 dimensions around the nucleus, we have an equal probability of finding an electron. A P-shaped orbital looks like a single set of lobes. We have a node through the center of the atom, so it's a spinning, kind of like an infinity sign. Then we end up with the directionality, where we're going to end up having 3 p orbitals on the 3 dimensions of our axes. I'll mention why there's 3 in a minute, but let's look at the D-shaped orbitals. The D-shaped orbitals have 2 kind of like nodal planes, so we end up having, one of them looks like this. So we have 2 sets of nodes instead of just 1 for the p orbitals. So that's our D. They look kind of like a butterfly or a clover leaf. The F orbitals just then have a third. So the F orbitals sort of, and there's a slide that'll show some of these, kind of have an extra set of lobes. So they kind of have 3 sets of lobes instead of 2. I may have missed one, yeah. So they'll have like 3 sets of lobes instead of P, 1 set, D, 2 sets, and then F have sort of 3 sets of lobes. So that's like our F shape. So all these orbitals here are different shapes. Then we have another quantum number that's going to tell us how many orbitals are possible with that particular shape. So the magnetic quantum number m sub L ranges from minus L to 0 to plus L. And so at some point we just have to, like once we start putting this together, hopefully this will make a little bit more sense. But if you imagine for a given n value, let's say n is equal to 2, then L could be equal to 0 or 1, but it can't be equal to 2 because the highest L can be is n minus 1. So the highest L can be is n minus 1. And then the m sub L depends on the L. So for the L0, the only m sub L would be 0. And when L is equal to 1, our m sub L would be equal to minus 1, 0, or plus 1. And so when L is 1, we get a range of m sub L's where there's 3 different possible values. And so remember, this is telling us this is our S shape, this is our P shape, and then there just being one orbital says there's one S orbital, so there's one 2s orbital, and there's going to be 3 2p orbitals. So the range of values here is telling us that there's 3 2p orbitals. So some terminology here would be that the n value is telling you the shell. So if we say the n equals 2 shell, that's all the orbitals and electrons that can fill into the n equals 2 shell. And then we can have a subshell. A subshell is just an n and L. So this would be a subshell. So we could have like a 2s subshell versus a 2p subshell. The 2s subshell has that spherical shaped orbital for which there's one of them. So there's one 2s orbital. So if we take these 3 numbers together, these are describing orbitals. So orbitals are described by an n and L, and they would have some m sub L value. And then the range of the m sub L's, the number of m sub L's possible with a given L value, would correspond to all the orbitals possible within that subshell. So I'd have 3 2p orbitals. So this would be describing the 2p subshell. There's like so much terminology we all need at once as we're still trying to understand what these quantum numbers mean and how they relate to each other. So let's go back to the n equals 2 shell is comprised of the 2s and the 2p subshells. Just for some terminology usage there. So if you have n equals 3, then the range of L values is 0, 1, and 2. So then we'd have the 3s, the 3p, and the 3d subshells. Now, we have a fourth quantum number that's going to describe the spin of an electron, and the spin can either be spin up or spin down. It can either be plus a half or minus a half. And so this is telling us that there's 2 electrons that you can put into one orbital, because each electron in an orbital can either be spin up or spin down. And then every electron in an atom has to have a unique set of quantum numbers. No two electrons can share an n, l, m sub l, and m sub s. So every electron in an atom has to have a unique set of quantum numbers. That's the Pauli exclusion principle. When I was coaching like third grade basketball, I used to tell the kids, if you understood the Pauli exclusion principle, you'd all stop standing in the same place. So electrons can't stand in the same place because they have a charge. So the charges repel, so the electrons can't be in the same spot at the same time. Hard to understand for third graders, but easy for electrons to understand because they have a charge, so two electrons can't have the same location. And so if you think of the quantum numbers, they try to describe the location electrons are going to use in the space that surrounds them. And so this is going to be a way to try to understand all the different configurations, the electron configurations for elements on the periodic table. So putting this together, we're going to try to understand there's a variety of n values, l values, m sub l's that are possible for all the different elements as they're filling their electrons into different types of orbitals. Okay, so we're going to go through and talk about each of the quantum numbers a little bit. So the angular momentum quantum number, that's the L that tells us the shape. And so this defines the shape of the orbital. The allowed values are 0 up to n minus 1. And the letters designating the shape. So S shape is from L1, P shape is L1, D shape is L2. There's some better pictures of orbitals that come up a little bit later. And then F shape for L3. And so the shape of the orbital is being defined off the L value. The m sub l, this is telling us about it's the magnetic quantum number, is the name of this quantum number, but it's telling us the orientation or the position that orbital points. You could think of this value, like we said before, it's minus L to plus L, all the integers and 0 in between. So again, if let's say L is equal to 2, then the range of m sub l's would be minus 1, or excuse me, if L is 2, the range of m sub l's would be minus 2, minus 1, zero, plus 1, plus 2. And so this is where we would get that there would be 5 different orbitals that share an L of 2. So the L2 would be describing a D shape. The first time you can have an L of 2, what does n have to be for L to be 2? N has to at least be 3. So the first time we can have an L of 2 is when n is equal to 3. So this would be describing our 3D subshell. So the magnetic quantum number is telling us about the projection or direction, that there's going to be 5 directions those orbitals can point. So we're going to see 5 different directions those d orbitals can point. And so for any subshell of an atom, there's 1 s orbital, 3 p orbitals, 5 d orbitals, f where L is equal to 3, minus 3, minus 2, minus 1, 0, 1, 2, 3. That's where we get that there's 7 f orbitals, and so forth. And we'll see that for elements in their ground state, we don't get past f. So for elements in their ground states, we're not going to be using any orbitals beyond an L value of 3. And so here's some different shapes of orbitals. So here we're showing the 1s, 2s, 3s for showing as n goes up, the size of the orbitals goes up, and the shape is just spherical. So there's one way to orient the sphere. So there's one 1s orbital, there's one 2s orbital, there's one 3s orbital. When you look at the P shape, the infinity sign type shape, there's 3 different directions that those orbitals can point. If you imagine those located on the axes surrounding an atom, we'd have the px, the py, and the pz. And so we'd have the px on the x-axis, the py is on the y-axis, and the pz is on the z-axis. So we have 3 different orbitals. So if we're talking about, say, the 2, n equals 2, L equals 1, so these would be the 2p orbitals that are being shown. So the 2px, 2py, 2pz. We probably don't use the symbols x, y, and z too much, but I just want you to think about the 3 different directions of the orbital, kind of, and the idea that the directionality of the orbital is what's being referred to by the m sub l. Now, the m sub l range, remember, minus 1, 0, 1. We're not defining which one of these is the minus 1, which one's the 0, which one's the plus 1, just that you get 3. Just that you get 3 from that range. And so one of these is referring to one of those orbitals, another one of those numbers is referring to the other. the d orbitals have the two sets of lobes, with the exception of this one here. We call it maybe the banana ring orbital, the d orbital. And so you can see two sets of lobes here for the d orbitals. Now what you're getting is two sort of planes where there's no probability of finding an electron. We call that a node. So this here, this is a node. So the p orbitals have one node through the center of the atom, and then the d orbitals have two nodes through the center of the atom. The number of nodes through the center of the atom, if you take note, is equal to the L value. So the L value is telling you how many nodes there are, and there's two nodes as well for even this orbital here called the dz squared orbital. So when you're trying to like sometimes we'll show you a picture of an orbital and say, what is this orbital of? Is it a d orbital? Is it a p orbital? This orbital here might look like a p orbital, but that extra ring, the position between the ring, anywhere you see like white space, is a nodal plane. So anytime you see that white space here, you have an axial, two axes that there is a nodal plane. So this is node 1, node 2. So I have two nodes still for that atom, so that's why that's one of the d orbitals. Now our textbook, for whatever reason, doesn't actually show the f orbital, so I grabbed this from some other source. The f orbitals just look like mostly three sets of lobes instead of two. So we see three sets of lobes. So we have three nodal planes between those sets of lobes. And you also see cases where you have some double nodes. So you see some cases where we have like two rings in addition just to one lobe. And so we either have two donut rings in one lobe, or we have three sets of lobes here. So those are f orbitals, and there are 7 of them. So I suspect our book doesn't show these because they're complicated and hard to see, but those are what the f orbitals look like. Then our magnetic spin is just saying that each of those orbitals that we just showed can have 2 electrons each. So the electron can be going in one direction or the opposite direction. So we can put 2 electrons into each orbital, spin up or spin down. So when I think of helium, helium's configuration has 2 electrons. The lowest energy orbital we can fill into is the 1s. So it's going to have 2 electrons in the 1s orbital. If we go back to hydrogen, just 1s electron, so I have a 1s2. For helium, a 1s1. For hydrogen, just 1 electron spin up. So helium has a spin up and a spin down, and hydrogen just a spin up or a spin down. We don't necessarily classify, again, the m sub s up or down as the plus or minus a half. And the plus and minus a half is actually more like aligned with the magnetic fields plus a half against the magnetic fields minus a half. So without an applied field, it's not even defined anyways. So the whole point I'm trying to make here is this is either the plus half or the minus 1/2. It's not really defined to be one or the other. So sometimes that's a little confusing. It's just sort of implying that we have one of the 2 allowed spins, and if we pair it up in helium, then we have the other spin of the opposite sign. So here we have one of them's the plus, one of them's the minus. And so from hydrogen versus helium, we can then start thinking of the electron configurations of our larger elements. So like lithium, beryllium, what do you think they want to fill their electrons into? Well, if you kind of notice there's a group of 2 elements, it would probably seem to make sense that that would be filling into a 2s. As we go to lithium, it would go from a 1s2, 2 electrons in the 1s, and then a 2s1. We have 3 electrons we got to fill in for lithium because it has 3 total electrons. And so it's going to fill in this way here. Beryllium coming next, 4 electrons, 1s2, 2s2. And so I'm kind of like almost using the periodic table as a guide to see that looks like what I call an S block, where there's 2 elements across. So I'm going to be filling those into an S block. If you notice, the next 6 elements across are kind of grouped together. Those elements there, boron through neon, must be filling into the P subshell. So as we go across boron, 1s2, 2s2, must be them filling into the 2p1. And then as I get to carbon, 1s2, 2s2, 2p2. So I'm just filling into the 2p subshell. I think this is on the very next slide, so let me continue along here with nitrogen real quick. 1s2, 2s2, 2p3. And let's start to think about how these electrons want to distribute into the different subshells. If we start to picture a diagram for like lithium, we'd have something like a 1s2, 2s1, 1s2, 2s2. So like thinking of a diagram of diagramming our lowest energy first, and then our highest energy orbital second. If I really wanted to do this, I'd probably be picturing the energy increasing for the orbitals, like my 1s, my 2s, those 2 electrons here, 1 versus 2 for lithium and beryllium. It's kind of thinking the energy is going upward for these orbitals. As the n value increases, the electrons are further away from the nucleus, they're going towards a greater energy. And so then I come across the p subshell, where I'm going to get all the way up to 6 electrons into that subshell. So as I'm thinking here, I kind of have 3 different energy subshells. If I'm thinking of this vertically, I might be picturing it kind of like this, where I have the 1s, the 2s, and the 2p subshells, energy increasing towards the upward. And so 1s2, 2s2, 2p1. And then when I get to carbon, what do you think it wants to do? Do we want to put 2 electrons together in one orbital? But this is where I start to think, well, let's try to picture what's going on top of just filling electrons into some goofy diagram. So let's imagine you have, for carbon, a 6+ nucleus. So we have a nucleus with a charge. We have the 1s2, the 2s2 electrons spinning around that nucleus. So I have 2 electrons pretty close to the nucleus. Of course, these are in some orbital that has some probability, but the probability is going to be closer to the nucleus than it is for the next orbital, the 2s. So I have 2 more electrons in the 2s subshell. So I have a 1s, I have a 2s subshell, and then my 2p subshell is in this region here. So I have a 2p subshell, 1 electron. And so imagine you're the second electron of carbon. Do we want to try to pack into that same orbital, or do we want to spread ourselves out? And I think you would probably say, let's use space as effectively as we can and spread out into a second orbital. So carbon uses 2 different orbitals. Let me show this more clearly real quick. That should have 3 distinct lines shown here to be referring to the 3 different orbitals of carbon, which would share the same energy. So we're going to use 2 orbitals, and this is called Hund's rule. So Hund's rule says maximize the spin of the electrons when possible. So when I'm filling into equal energy orbitals, pair the electrons together, use multiple orbitals when possible. For nitrogen, 3 electrons in, that's really good because I'm going to end up with a configuration where I have all 3 electrons spin paired in the same direction. And so for carbon, I have 2 unpaired electrons. Boron has 1 total unpaired electron. Nitrogen has 3 unpaired electrons. These are paired electrons, so when you have a spin up and a spin down, those are paired. So whenever you have net unpaired electrons, we count those as unpaired. You'll see a lot of questions will ask, how many unpaired electrons does a certain atom have in its ground state configuration? Just because getting this answer right will tell us if you have the right configuration. So if we get all the way across to oxygen, so 1s2, 2s2, 2p4. So for oxygen, we have to start spin pairing. So oxygen would have 2 unpaired electrons. Fluorine would have 1 more electron, so it would have 1 unpaired electron. I'll just cap off writing neon, so I'm skipping fluorine. So getting all the way to neon, 1s2, 2s2, 2p6, we finally arrive at a good picture for why neon is so stable as a monoatomic gas, because it has no unpaired electrons, it has no room for more electrons, it's going to have a tough ability to give up an electron. We'll see that in chapter 7 later, but we have 0 unpaired electrons here. So we cap off our subshell 2, so we completely have filled our n equals 2 subshell as well. So our n equals 2 the n equals 2 shell is the 2s and the 2p subshells, and we've completely filled both the 2s and the 2p subshells here. And so we're going to see that's the case for all of our noble gases, that they've completed their subshells and completely filled them with electrons. Skip to the next slide. Oh, actually this slide is here. And so this slide here is just showing us the combination of n values for a given shell. So we went through 2 already, so the 2s, the 2p subshell. So what's going to come next in the periodic table, you would probably guess would be the 3s and the 3p subshell. So the 3p subshell is the L1, the range -1, 0, 1. So we have 3p orbitals. And then presumably next is actually going to be the 4s. If you look, potassium, calcium kind of come next in terms of relative energy. The periodic table will help us understand the order these orbitals are filled. And then we go to the 4s, and then we'll circle back to the 3d after we fill the 4s. So if you notice, after we go from potassium to calcium, we then fill 10 elements across. That's filling into our 3d subshell, 10 orbitals across, 5 orbitals total. And the 4f subshell, if we were to go through it, 4s, 4p, 4d, 4f subshells. So we're going to have to see as we kind of continue past the periodic table, like Let me see what my, so we'll just end with the idea being, once you get across neon, we get across to argon. We'll talk about that as we continue. We're going to try to get across from potassium to krypton, just understanding electron configurations. And it's kind of continuing the periodic table and thinking of it as our guidepost, the orbitals, and some of their quantum numbers as our guideposts as well, as we try to think of these electron configurations for our atoms. So that'll do us for today. Have a great weekend. Slide is just to end on here.